Dear students and participants of this course, Railway Engineering, today we are going to move forward and we are going to talk about track modulus and relief of stresses. If you remember, in the last class, we have discussed about various types of numericals which can be there with respect to hauling capacity and the resistances which are offered by track in terms of rolling stocks or the track profile, geometry, or even the atmospheric conditions, maybe the wind. Now, in today's lecture, we are going to talk about the track modulus, the relief of stresses, and the lift of rails. So, these are the three topics which we will try to cover in this lecture. So, let us start with the track modulus. Now, track modulus is based on the elastic theory. Now, what is track modulus? It is an index which provides the measure of resistance to deformation, and thus the stiffness of the track can be identified. So, we have a track, a rail section is being provided, and below that there are sleepers, and then there is a wheel at the top of it which is moving in direction. Now, because of this wheel, there is going to be some of the deflection here, and that deflection will also go in the lower layers. That is what is the meaning of the elastic theory. So, what it says is it provides a measure of the resistance to the deformation. Now, deformation here, when we are saying, we are more interested in looking at a deflection, because if it is a total deformation, then that can become a distress. And if this deflection is not much, it means the total system which is being provided, including the ballast cushion at the bottom or the packing on the sides of the sleepers, this total system is having a good stiffness. So, the track needs to have both of the things, the elasticity as well as the stiffness. And how we define this value? We define it as load per unit length of the rail, which is required to produce a unit depression in the track. So, whatever this depression is there, if we take say as 1 unit, and there is a load P which is acting here, and because of that load this depression has occurred. So, in this total rail length which is provided, so it may be like 13-meter long rail. So, when you are talking about this 13-meter long rail, then whatever the total deflection is going to be there, we take it as a average condition with respect to the this whole length. So, that is why we get it by dividing by 13-meter. If say we talk about, it will be a unit length of the system. And what are the units? The units are kg per centimeter square or pounds per square inch. Now, this track modulus, it can be of two types. One is initial track modulus, another one is elastic track modulus. Now, as the name itself says, elastic track modulus, that means everything in this particular domain is going to be elastic in nature. So, if we talk about say the steel and we go for a stress and strain conditions, so as you increase the values, something like this is going to happen. That is the strength curve which we draw. So, we are saying that we are in an elastic condition. As the stress is increasing, then there is a increase in the deformation here in the terms of a deflection, and then if it is being removed, it will come back. But then what is this initial track modulus? So, let us look at why there are two values here, and both of these two values they are used in the design. Now, when you talk about the initial one, how we can differentiate it? The rail depression immediately below the rail seat is not directly proportional to the load in its entire range. That means, when we have created this diagram and we said that it is going in this form, it is not so. Initially, it is going to show more this type of a behavior, and then it becomes straight. That means, the the initial conditions, the depressions is going to be a bit more. Now, why this depression is going to be a bit more is the point of discussion here. Now, when we talk about the loading, as I said, there is an initial loading and then there is further loading which takes you into the elastic range. A linear load depression relationship exists in the initial stage of the loading. Now, what is happening here is due to the slackness and air voids in the track structure, the track depression is higher in the initial stages of loading. Say we are talking about, as we have just drawn at the back side, that this is a rail and it is having a sleeper at the bottom. If by any chance these fastenings are a bit loose, then there is going to be a play here at the rail seat. Similarly, this sleeper is being supported by the ballast, and if there is a issue with the compaction of the ballast or there is a looseness in the ballast, then whatever loads come in terms of the wheel, it will cause a sort of you can say that it will just seat down, it will come down, and similarly this sleeper will settle inside the ballast. So, this is what is an issue here. So, that is what it says, whether there is a slackness or there is an issue with the air voids in the structure, in the ballast, etc. Then as soon as the loading is being done, the depression is going to be more. And this initial higher track depression is, you can further say, is because of the gap between the rail and the sleeper at this point, or between the sleeper and the ballast, say at here, and the voids within the ballast. So, there are voids here and there can be a gap at this point or gap at this point. So, as soon as the initial load has been applied, the settlement will take place. Now, this everything will get rearranged, recompacted, and you will find that there is more of a value of a depression which has come up. Now, this slackness is also governed by the state of the maintenance of the track. If the track is not being maintained in the right manner, periodically is not being charged and being maintained, then the slackness or the gaps or the voids in the ballast, they will be more. Now, this initial load at which the higher depression occurs is known as the seating load, and this is taken as 4 tons for the broad gauge and it is taken as 3 tons for the meter gauge. And this seating load which of 4 tons or 3 tons actually is giving you the initial track modulus. So, at this particular load, whatever is the depression, and if this depression is being taken in terms of now finally the values which are being taken as kg per centimeter square, then that is the track modulus and this is the initial track modulus. Now, after this loading, the gaps have got reduced or maybe there are no gaps being left. Similarly, if there are voids, they will get closed up because the aggregates will come more nearer to each other, and the application of further loading will result in a smaller depression per unit load. So, now it is a change. Initially, the depression, if we were talking about the depression here in this form, so it was larger at a smaller load, but then it starts going in this form, and what you found is now this is how the values will change in a proportionate manner. So, beyond 4 tons, in the case of broad gauge, the track modulus is in the true elastic range and this is called the elastic track modulus. So, the first one which we talked as initial is related to 4 tons of load in the case of broad gauge, and then as we increase the load beyond this one, by whatever delta p value, it will take us to elastic track modulus condition. The stresses computed based on these two track modulus are found to be more realistic in nature, and the both are being used in the design. Now, when you talk about this track modulus, what are the factors which will affect the track modulus? As we discussed, there is a overall total component system which is there in the case of track or a permanent way, is starting from the ballast, at the top of which the sleepers are being placed, and then at the top of that sleeper we have the rail section. So, this total system is already there. So, that means now what are the factors which are going to make a difference is, if we start from the bottom. So, what type of ballast is being used, and then what is the depth of this ballast. So, this is cushion. This we have already discussed when we talked about the permanent way. So, type and the cushion of the ballast, this is going to make a difference in terms of the track modulus. Then another thing is, at the top of that we have sleeper. So, what type of sleeper is being used, whether it is a wooden sleeper, it is a cast iron sleeper, or it is a steel trough sleeper, or it is a concrete sleeper. So, which particular type of sleeper is being used, that will having a different strength parameter. On the basis of those characteristics, the track will be having the modulus value. So, this is another aspect. And then at the same time, when we are talking about this sleeper, at the top of which the rail is being provided, how many sleepers are providing? So, you have a rail and then sleepers are being provided like this. So, what is sleeper density? We discussed about the sleeper density and we said this is being shown as m plus x, where x can vary from 4 to 7. So, this is another case. So, type of the sleepers and the density of the sleepers is also going to make a difference in terms of the track modulus. Then when you come up, we have a rail section. Which rail section is being used? Even if say we have talked about the flat footed rail, within flat footed rail is it 60 kg or it is 52 kg, it is 90 R, or it is even more than 60 kg, 68 kg or 73 kg per meter rail section. That will also give more track modulus. As you go down, the track modulus is going to be reduced. So, this is another aspect which will be there. Now, all of this ballast cushion is finally resting here. So, there is a subgrade here which we have previously also discussed in terms of a formation. So, what type of formation is there? What are the characteristics of this formation in terms of the strength parameter? So, what is the bearing capacity? How much load this formation can take? Is it a yielding formation? It is a non-yielding formation. So, that type is also going to lend some support to the track modulus. Apart from that, because we are using the rails, so what is the gauge which we are considering here? If we are talking about a broad gauge or we are talking about meter gauge or a narrow gauge, as you go from meter gauge to narrow gauge, the track modulus values will be changing, will be reducing. So, this is also an important point here. And then finally, as we talked about previously, the track maintenance. Now, this track maintenance, if it is not being done, it may create a problem in the area of a ballast cushion. It can create a problem in terms of the sleeper and the rail fastenings. It may have a problem in terms of the rails where the gauge is not being maintained, or there are sways or movements there because of those poor maintenance practices being followed, and that will also create a negative aspect towards the track modulus. So, all of these things are going to make a difference together. They are not going to just work as independently. They are all together going to create an impact and we will have a change. Now, what are the various recommended values? Now, in the case of broad gauge tracks or 90 R rail with n plus 3 sleeper density and 200 mm ballast, Okay, as we have discussed in the previous slide that there are so many factors, but all these factors are going to work in combination with each other. So that is why we are talking here sleeper density, we are talking about ballast, we are talking about the rail section, we are talking about the broad gauge. So in this case the initial track modulus is 75 kg per centimeter square and the elastic track modulus is 300 kg per centimeter square. But from 90R rail, if we change to 52 kg rail and we improve upon the slipper density as n plus 6 and ballast cushion has been increased to 250 mm, which is the minimum ballast cushion which can be provided in these particular cases, that in that case what happens, the initial track modulus increases from 75 to 120 kg per centimeter square and the elastic track modulus, it increases from 300 to 380 kg per centimeter square. Now, if we talk in terms of a meter gauge, where 60R rail or 75R rail is being used and plus 3 slipper density is being taken and 200 mm of ballast is being provided, then the values are further down. The initial track modulus reduces to 50 kg per centimeter square and elastic track modulus reduces to 250 kg per centimeter square with respect to 75 kg and 300 kg per centimeter square in the case of broad gauge track. Now, how can we compute this value? So, what is the experimental way of doing it? So, what we do is we observe the deflection below the sleepers. So, you have a rail section and then below that section we have the sleepers being provided. So, when these sleepers are there, so we will take the length and with respect to that length all these sleepers we will get a value of delta, delta 1, delta 2, delta 3, delta 4, delta 5 and so on. Now, track modulus can be calculated as mu is equals to P divided by delta into L, where delta is the average deflection for all of these sleepers starting from delta 1 to delta n, whatever number of sleepers are being provided below the rail length. L is the rail length and P is the load which is coming on one rail. Okay, because there is a rail here and there is a rail section here and we have a axle with a wheel combination at this point and a wheel combination at this point. So, whatever load comes on the axle as P will get distributed on both sides and this will be P by 2 here and P by 2 on the other side. So, that is why we are taking it in that form. We said that it is on a one rail. So, this track modulus is P divided by delta into L. This is one way. And as I said that this average deflection is nothing but sum of the deflections under the sleepers divided by number of sleepers. Say if we take a summation as summation delta I, where I is the number of sleepers which have been used and n are the total number of sleepers. So, if it is goes to n, so delta is summation delta I divided by capital N. Now, if we put this value with in place of delta in the formula which we just talked about, that is mu is equals to P divided by delta into L, then here this is P divided by summation of delta I divided by n. So, n will come at the top, it will become numerator part and then divided by the length of the rail. Now, here when you talk about this length of the rail divided by n, that is this value, this becomes nothing but this is an average spacing between the sleepers. Therefore, this formula can further be changed as P divided by summation of the deflections below the various number of sleepers on a one rail length multiplied by the spacing of the sleepers. So, this gives you a possibilities that what are the way you can calculate the track modulus very easily. Now, let us look at one of the numerical here. We have a locomotive which has 19.5 tons of load on one axle wheel combination. The length of the rail is 13 meters. The initial track modulus is given here as 0.075 tons per centimeter square or 75 kg per 70 centimeter square. We have to calculate the deflection which is being caused below the load on the rail. So, the average deflection which is going to be there in this case, we are working with this formula, that is initial one, mu is equals to P divided by delta into L. So, P is being given to us as 19.5 tons, L is given as 13 meters. So, in centimeters 1300, and the delta is to be identified, whereas mu is given as 0.075 tons per centimeter square or 75 kg per centimeter square. So, if we put these values, we will get a value of delta here, and delta in this case comes out to be 1 mm. So, this is the total deflection, or basically the average deflection, you can say, instead of say total, then total divided by n you have to do. So, it is an average deflection which is being caused on the rail because of this loading. Let us have another numerical here. Here the locomotive has 18.4 tons of load on one axle wheel combination. The length of the rail is 13 meters. It is a broad gauge track. The deflection caused below the load on the rail is 0.22 mm. Calculate the track modulus. So, here again the formula we are going to use is the same. We have to calculate the track modulus mu. The load is known to us, the length is known to us, the deflection caused on one rail is also being known to us. So, if we consider this, so it is 18.4 divided by 2. So, that is the load which is coming on one rail, then divided by the length in centimeters and the deflection being given to us in centimeters. So, what we get finally is 0.321 tons per centimeter square or 321 kg per centimeter square. Now, if you remember that this type of a value which has being discussed as the recommended values of initial track modulus or elastic track modulus, this falls in the category of the elastic track modulus. So, this is another simpler numerical which can be there in these type of cases. Let us look third one. Again, a locomotive has a load of 18.4 tons on one of the axle wheel combination. It has 3 driving wheel pairs. The length of the rail is 13 meters. There are 20 sleepers per rail length. So, a sleeper density is already being defined in this form. The total deflection caused below the sleepers is also given 1 centimeter. Calculate the track modulus. Now, in this case, because we have been given the number of sleepers, so we are working with this formula with P into N divided by summation of delta into L, and the total deflection which is being caused is 1 centimeter. This is summation of delta only. So, the values comes here. We have the total load which is 18.4 into 3, because 3 driving wheels are there, multiplied by 1000 multiplied by 20. So, tons has been changed to kg conditions, and then 20 is for the number of sleepers, and summation of delta is given here, that is this 1 centimeter. L is the length of the rail which is 1300 centimeters, and because this load is coming on both of the wheels, it is being divided by 2. So, finally, what we get here is 424.6 kg per centimeter square. So, again this is a elastic modulus range which we have got in this case. Let us have another one. Here again the load is the same, 18.4 tons on one axle load with the having 3 driving wheels pairs. The center to center spacing is given as 65 centimeters. The total deflection caused below the sleepers is given as 1.22 centimeters. Now, again the track modulus has been calculated. So, the third formula which we created, where the L divided by N has been used as a sleeper spacing S, is being used here. So, this is P divided by summation of delta into S. So, the load up to this point, the load is being taken up for per rail, and then summation of delta 1.22 and the spacing is 65. So, we get a value of 348 kg per centimeter square. So, this is how the track modulus under different conditions, what type of data is been given to you, you can calculate. Now, let us come to the next topic, that is relief of stresses. Now, relief of stress is what? This is a state that is reached when a group of wheel loads working close to each other act simultaneously on the rail. So, we have a rail section and there is a wheel here, and then there is another wheel, or there may be number of wheels which are there. So, they have center to center spacing say SS, and the loads are coming on the top of these wheels because of the wheel axle arrangement. So, there is going to be some issue here because of this wheel the deformation will be there. Now, when this deformation is there and this deformation is going downwards and if say positive is a value, then what will happen that because of this deformation there is this type of wavy action is going to be there. There is a lift of the rail here and whatever the stress is on the other side will be the negative. Now, because of this another wheel also the similar things will happen. Now, how these combinations are creating an issue, that is what we are going to discuss. So, first of all we will be talking about a single wheel case and then we will be going into the more than one wheel case. Now, what it says, when a single wheel load acts on the rail deflects at that point and a maximum bending moment gets produced below the center of the rail seat. So, below this center of the rail seat we are going to have a maximum bending moment. Now, this bending moment becomes negative after the point of contrafracture. So, when we are talking about a bending moment, so if this is a case of a bending moment, obviously at this side or as this side it is going to be other profile. So, that means it is going on the other side of the line if we are taking this as a datum line where the load is being applied. So, this is a positive bending moment if we are considering, then obviously this is a negative bending moment which will be caused. So, the bending moment becomes negative after the point of contrafracture. It attains maximum negative bending moment at some distance from the wheel load. So, there is some distance x at which this is going to occur. And this negative bending moment which is produced here becomes negligible at a further distance because it will subside in this form. So, here this is a maximum value. So, this is a case positive and a negative bending moment case we are basically talking here. Now, this is same thing is shown here, we have a rail length here, there is a wheel load coming on this side. So, some P load is being applied and because of that the positive bending moment has got created. But if we draw the overall this curve of the bending moment, then there is a point after which it takes the change in the nature and it becomes negative bending moment and it is maximum negative bending moment at this point, which is what we are talking here, that there is a distance x at which it will happen and finally it is becoming negligible. Now, let us talk about the group of wheel loads, what is happening. So, we have understood that if there is only one wheel, then how the bending moments are going to be created and where the positive or the negative moments will be there. Now, we are going to apply two wheels or more than two wheels and see that what will happen. In the case of group of wheel loads, the maximum positive bending moment produced below the center of rail set on which the wheel load under the consideration is acting gets counteracted by the negative bending moment produced by the adjacent wheel load. So, what is that? Here previously we talked about one, now we have two such cases. So, there are load 1 and load 2. For the load 1 this is positive bending moment number 1 and there is for load 2 this is positive bending moment number 2, but at the same time there is a negative bending moment which has been caused and this negative bending moment in the first case this is -1 I can write. So, this is how it is going. For the second one this is -2. So, what you can see is that there is some positive value which is coming up to here, that is the ordinate, but in the case of a previous wheel there is a negative bending moment which has acted here and therefore, the overall total bending moment at this point is positive minus negative. So, this is a total bending moment which will happen. So, the value has reduced here and because this value has reduced, that is what is the relief of stress which will be there. So, what it says is the net bending moment under the wheel considered will be less than the maximum positive bending moment and that is how there is some relief in overall structure of this system. Hence, the magnitude of the relief of stress depends upon the distance of the point of contraflexure of the rail and the spacing of the wheels. So, point of contrafracture is here and the spacing of the wheels is being taken like this. So, with respect to this point x and the spacing s. Now, if this happens beyond, then obviously where the positive bending moment is caused, if it is coming at the negative bending moment maximum side, then only this relief is there, or otherwise if it is shifting either this side or the other side, then the relief will not be maximum. So, that is why these two parameters are going to create an impact. Now, in case of the wagons, the axle distances are very large as compared to the axle distances of the locomotives. So, there you will find the differences may not be coming in that form. Also, the stresses due to locomotives are higher as compared to the wagons because of heavier weight of the locomotive. So, the conditions of relief is probably going to be more in that sense, and this relief of stress under the wheel can be as high as 50%. So, whatever positive bending moment is there, the negative bending moment can be half of that, and that is where the relief will be by 50%. The third thing which we were supposed to discuss is a lift of rails. Now, we have discussed that because of the wheel there is a depression, but then depression goes forward in this form, or maybe at the backward side also it goes in this form with respect to the level of the rail. So, we have this as a level of rail, and then the wavy pattern is getting created because of the application of the load and which the load which is moving. So, due to the wave like action in the rail and the passage of the train, the rail tends to bend upwards at some distance ahead of the leading wheel. So, if this is a leading wheel, at some distance ahead there is a wave being created, and it is assumed that the rail supports are capable of developing negative reactions to counter the wave effect. Now, this wave effect is going to be countered by way of the sleeper being provided at this point and the connectivity of the rails. So, if they are good, then this is going to resist it. However, the play between the rail foot and the dog spice or the other fastenings which have been provided, they permit the lift of the rail, and this causes an increase in the bending stress in the rail by 10%. So, this pattern, if the packings here are not good enough, then it may increase the bending stresses. Previously, we talked about the relief. We said that at this point there is going to be a relief because a negative bending moment is also there, which is being caused due to the adjacent wheel. But here we are saying that if these loose packings are there, then there is a stress building, and that stress building is by 10%. Now, if the condition of the sleeper of the ballast cushion is bad, then the increase in the stress can go beyond 10%. So, it is furthermore, and this happens to all axles which are spaced at a distance greater than 6x, where x is the distance from the load to the point of contrafracture of the rail, which is what we have discussed previously. So, this is the distance x which we are talking here. So, 6 times of the x if it is there. So, if they are all those axles which are spaced at a greater than this distance, then this lift condition will be there. If they are nearer, then because of the negative bending moments being caused, the reliefs will be there and the lifts may not be there. So, with this we close our discussion. What we discussed was the concept of the track modulus as the initial track modulus and the elastic track modulus, and then we talked about the relief of the stresses which are caused due to the multiple moving loads which are acting through the wheels, and then finally the lift of the rails. Thank you, and we will be meeting in the next lecture.